for theory of relativity. As I mentioned to you in the last session, he got it for explaining photoelectric effect. In fact, more than that, photoelectric effect can also be credited with not just growing and giving, kind of germinating quantum mechanics, the field of quantum mechanics, but rather also, in addition, establishing the field. All right. So let's get over with the formalities. Let's get over with the greetings and let's start with this session. Right. So what do we see here? Right. We have this setup over here made, and in this setup over here, we can see that we have we have basically a discharge tube, and we have connected it to an ammeter, to a battery, right? Forget about the torch for a minute. Okay. Now, one more thing that is not mentioned over here is that we have tried to create almost perfect vacuum here. But the key word is almost perfect vacuum here. So we'll be rather referring to this thing as partial vacuum here. Okay. I'll get to the bit why we need vacuum here in a bit, and I'll also get to the bit why we need the battery here also in a bit. Just hold for a minute, right? Okay. Now notice one thing, right? These two electrode plates, right? You've kind of removed all the gas molecules in between, and there is no contact between the two plates, correct? Now the point is, if there is no contact between the two plates, right, this circuit here is incomplete, right? Then why is it happening that when I am shining a certain radiation on one of the plates, I'm getting a reading? Right? What is happening over here? Right? So the point over here is, now, first, before I enter into that logic, right, I want to actually tell you something, right? So, in fact, I want to ask you something. So, let's try to recollect what we know, right? So, we know that metals are good conductors, right? And we also know that electricity is the fundamental unit of electricity is an electron, right? That is how they got the name, as we have discussed in the first session. Now the point is how or why a metal is a good conductor of electricity is because of loose electrons, loosely held electrons, right? Those electrons which are not as tightly held by the nuclei, right? They can move around and they can essentially what? Be the conductors of electricity. Okay. Let's hold this discussion at this very point, right? Okay, cool. Now I want to bring in another analogy over here. I'll establish this analogy, then I'll come back over here to the loosely held electrons, right? Okay. So let's say I have this ball here. I throw it up in the air, right? What happens? It goes up, momentarily stops and comes back. Now the point is, this kinetic energy of the ball is being utilized to fight against the gravitational pull, right? It is working against the gravitational pull, and thus, as a result, it is getting consumed, right? It is getting consumed. Now, the point is, right, you can also see it here, right? It goes up and up and up. Kinetic energy gets consumed and consumed and consumed, and there comes a point of time where kinetic energy becomes zero. There is no more kinetic energy to be utilized to work against the gravity. And so this ball momentarily stops and then gets pulled back by the gravity. Now what if, right, you were a superhuman? What if you provided this ball with so much kinetic energy that this ball, right, went up and up and up, crossed the Earth's atmosphere, entered into space. Still, this ball was feeling certain gravitational pull. Right? Okay. So this ball kept moving further and there was certain a pull. So it kept decelerating. It kept slowing down. Eventually a point came wherein we can say that theoretically at that point in space, the gravitational pull of Earth on the ball has become negligible. Or theoretically we can say it has become zero. And no other pull is there on the ball. And let's say we had provided the ball with so much energy that even at that point, the ball was still left with some kinetic energy. Right? So the point is, beyond this point, since there is no force on the ball, The ball will keep moving beyond this point with a constant velocity, constant speed. Right? You understand, right? There is no more pull on the ball beyond that point at which the gravitational pull of the earth has become negligible. So there is no force, there is no deceleration. F is equals to 0. So A is equals to 0, F is equals to ma. Correct? Now, since no acceleration is there, no deceleration is there, the ball will keep moving forward, right, with a constant speed as it had at the exact moment where the gravitational pull of the earth became theoretically zero. Now think about this, what is happening over here, right? Let's say this radiation is coming, and on this metal plate, the loosely held electrons, right, they get that energy. Right? They get that energy. They take that energy. Right? They try to move away from the nucleus because nuclei are pulling them, right? They are keeping them together. They are holding them. Right? So they take that energy up and they try to move away from the nucleus. Right? Nuclei. They try to move away from the nuclear pull. Right? And if they reach a point at which the nuclear pull becomes negligible, beyond that point, if they are left with any more energy, that becomes their kinetic energy. So let's take some hypothetical number. 10 minus 6 is equals to 4. Right? Remember this, we'll be referring this a lot. So let's say I'm just assuming some hypothetical numbers. Let's say 10 units of energy, right, was provided to a single electron. I'm not saying 10 joules, I'm not saying 10 calories, I'm not saying 10 ergs or whatsoever. I'm saying, let's say 10 units of energy was provided to this electron, right? While moving out, right, to move away and out of the nuclear pull, it required 6. So, right, just like the ball slows down, right, 6 of that 10 got consumed in getting out of the nuclear pull, and the remaining 4 became its kinetic energy. Right? So this was the energy provided, which is basically what, similar to 10. This is the kinetic energy of the electron once it gets out of the nuclear pull. But what is that W naught? Right? This W naught here is called as work function. Right? This W naught is called here as work function. Remember what this 6 was? This 6 was the energy the electron needed to get out of the nuclear pull. Right? So that is what it is. Now work function is essentially defined as the minimum energy required to pluck one electron out of the plate, right? Or pluck might not be the correct word. The minimum energy required to remove an electron out of the plate. Alternatively, it can also be phrased as the energy required to remove the most loosely held electron on the plate, on the surface of the plate. Right? Okay, cool. So this is represented as either W naught, and many times it is also represented as phi. So this is also another representation for this thing. Right? Okay. Now this electron, right? This electron travels to the other side. Right? We have basically, I'm coming to the battery logic, right? This electron travels to the other side and thus completes the circuit, and therefore we get a current reading. Okay, this emission of electron because of we have read about photons in the last class, right? Okay, so this emission of electrons because of photons being incident, right? So this emission of electron is called as photoemission, and the current that we get as a result is called as photocurrent. Now, the point is, the electrons here, right, they get released in all the possible directions, right? So as to streamline them, right? Okay. So as to streamline their uncontrollable random direction emission, right? So as to streamline all of them, we have installed a battery over there. Also, we have tried to clear the space between the two electrodes so as to reduce the obstacles for electron emitting from one plate and reaching the other plate. We try to reduce the obstacles, right? Because these electrons might collide with the gas molecules in between and lose some of their kinetic energy and might not reach the other plate, right? That's why we are talking about a vacuum over there. Okay, fine. So this is one thing. Okay. Now the point is, right? The crazy thing is, I'm getting into the details one by one. The crazy thing is, but why is this so difficult? Why did Einstein got a Nobel Prize for explaining the functioning of this? So the crazy thing is that over here, right, basically this happened only for a certain radiations. Let's say we had a certain metal plate and let's say for that metal plate, so we have fixed the metal plate, right? So we have also fixed the work function, right? Because work function is a property of the substance, of the electrode. Okay, obviously. Now the point is, this was only happening for certain radiations, as in let's assume that for a certain metal, when we incident the red light over there, we did not get any emission, right? And now in that particular case, whether we took a bright red or whether we took a dull red, right? However bright we took, we did not get emission. We thought maybe red is a weak radiation, so let's incident a bright red so as to provide more energy. No emission, no photo emission. We thought, okay, maybe we will incident red for a larger duration so as to provide more energy to the electrons. Again, no emission. Right? So this was confusing. This was confusing, right? So at the same time, what happened was Einstein, right, was also Einstein, Planck, black body radiation. All of these things were happening almost in the same time duration. So Einstein tried to implement Planck's quantum theory that light is considered light consists of tiny energy packets called as photons, right? The dual nature of radiation, remember from the last session. And he said, what if, right, at a single point of time, only one photon can interact with one electron, right? This is not something that Einstein said, one rule to remember. In fact, when you go into a higher grades and you, let's say in bachelor's or master's or PhD, you read more about it, you will come to know that in some cases there might be exceptions to this particular rule, right? This is for an ideal case. This is for our curriculum. This is for a broad level understanding. So let me get to the point, right? So always remember, one photon will interact with one electron. One photon, one electron, one interaction. Always remember that. Now, how does that solve the problem? That solves the problem how? Let me illustrate it, right? Okay. So, let's say my electron required 6 to get out. Okay, fine. And let's say you provided it 10. Okay, fine. And the kinetic energy was 4. Correct? Okay, fine. Now, the point is, let's say your photon, right, the red photon was of energy 5. And the required energy was 6. Right? And so over here, we are not going to have any emission. Why? Why? Right? Because your individual photon, which is going to interact with a single electron, is not sufficient enough to cause the electron's emission. Now, remember we took a brighter red, right? Brighter red. Now, it doesn't really matter whether you take a lot of red photons and throw at the plate. Doesn't matter. Because all those lot of photons of what are going to do, they are going to interact with separate electrons, right? That is basically, that doesn't concern the single electron that this one photon is going to interact with. Let me clarify, right? Okay, just hold on here a minute. So let's consider this thing. These are the things that you do not have to do, right? Do not have to do. What will not happen? What will not happen is, let's say I had this equation. Let's flip those numbers over there. Let's say 4 was required and 6 was the kinetic energy. So what will not happen is, this photon of energy 10 will not divide its energy into 5 and 5 and provide it to 2 different electrons and cause emission of 2 electrons. Not happen. Okay. Let's consider a different scenario. Let's say essentially we had something like this over here and we did not have any emission. right? Okay, fine. So the point over here is what will not happen is that two photons will not combine their energy, become 20 and provide it to a single electron. This will not happen because why? We have one photon, one electron, one interaction. Remember this. Okay. Now the point here is that whether you send 100 photons or 1 million photons, right? Whether you send a dull light or a bright light, right? That is what the meaning is. We'll come to this towards later in the section, right? But I need to introduce this right now. So whether you do this or whether you send 100 photons or 1 lakh photons or 1 million photons, right? It is not going to matter. Because ultimately, one photon is going to interact with only one electron. Whether you send the same army of photons for a longer duration, nothing is going to change because ultimately one photon is going to interact with one electron. Right? So remember this, and that is how kind of Einstein helped explain the photoelectric effect and got a Nobel Prize for it. Okay. Now the point is, right, essentially with this in mind, what we can do is we can modify our equation. We can say that this is energy of a single photon, right? This is the work function, and this is obviously the kinetic energy, where this is the mass of electron and this is the speed of the emitted electron, photo emitted electron, right? It can also be called as photoelectron. Okay, right? Also, what we can do over here is we can represent it by phi. Also, since this is energy of a photon, we can represent this as h nu, and we can also represent this as hc by lambda. All right, okay, fine. I can already see, right, if basically I'm using a highly energetic photon, right? Basically, let's say instead of 10 minus 6 equals to 4, let's say I'm using 20 minus 6 equals, then I have 14. So I have a highly energetic electron coming out. I have a faster electron coming out, right? So as you can see over here, right, if you basically consider this, let me do a quick recall, right? Which one of these, red or violet, has a larger wavelength? Obviously, red has a larger wavelength. Which one of these has a larger frequency? Violet has a larger frequency, right? So frequency of violet is more than frequency of red, correct? So energy of violet is more than energy of red. So you can see here why in the case of red incidence, right? Let's say in this metal, the work function is low enough that even red is causing emissions, right? Do not confuse it with the example we considered earlier. So with this, we are having slow electrons. With the violet one, right, at the bottom over there, you can see why the violet one is emitting fast electrons, and whereas yellow somewhere in the middle is basically emitting electrons in between. Now, tell me something. If I double the frequency, listen to it carefully. I'm asking you a question, right? This is a question. This is an oral question I'm asking. If I double the frequency, the kinetic energy will double. Is this a correct statement or not? Okay, so the point is essentially if you look here, right, if you double the frequency, look here at the corner, right, at the left middle corner, okay, if you double the frequency, the energy doubles. So it is an example like this, right? But did the kinetic energy double? No, right? Obviously no. So basically we cannot directly say that the energy of a photon is directly proportional to the kinetic energy. No, we cannot say that, because doubling the energy of a photon or doubling the frequency does not double the kinetic energy, right? Not double. So it is obviously dependent on that. If this increases, that increases, but they are not directly proportional, right? This could be a statement of an objective question. Okay. So what are the points to remember? When a photon of sufficient energy strikes an electron in the atom of the metal, it transfers its energy instantaneously to the electron during the collision, and the electron is ejected without any time lag or delay. Remember this, although we have already understood this. Greater the energy possessed by the photon, greater will be the transfer of the energy to the electron, and greater the kinetic energy of the ejected electron. Perfect. Again, we have studied this. Now, threshold frequency and threshold wavelength, these are two terms that we have to, kind of get comfortable with. Okay, so let's see about this, right? So let's say we essentially the electron required 6 and we also provided 6. In that particular case, the kinetic energy of the emitted electron will be 0, right? Now, if you transfer this in the equation formats that we have developed, right, we basically can say that you have provided work function equivalent of energy. Understand? We have provided work function equivalent of energy. We can also say that essentially, right, the frequency that you have provided, right, basically that is almost that energy of the photon is exactly equal to the work function, and so this frequency is called as threshold frequency, and in a similar way this wavelength is called as threshold wavelength. Understand? Same thing. Okay. So this is the frequency at which the energy of the photon is exactly equal to the work function. This is the threshold wavelength, is the wavelength at which the energy of the photon is exactly equal to the work function. Okay, fine. Now here, think about it, right? This is what we have. Now I can actually basically say something like this. I basically apply a naught to it. For threshold wavelength and threshold frequency, we apply a naught over there, right? Okay, so remember this. Now I wanted to convey something, right? Let's say we were dealing with the 10 minus 6 is equals to 4 example, and let's say we are talking about energy here. Right? Let's say we are talking about energy here. So let's say we had energy provided 1, we did not have any emission, 2, any emission. We could also have 2.3, 2.4, any number over here, right? As long as that is quantized to some smaller number. Let's say we provided something like 3 or no emission, 4 no emission, 5 no emission, 6 we got the emission. And every other value that is 6 plus, we will get the emission, correct? Okay. Now we know that energy is proportional to frequency, right? So basically, let's say we started with this lower frequency, lower frequency, lower frequency, lower frequency, no emission, no emission. First time we get something, right? And every other frequency above this frequency, we are going to get an emission, right? This is basically what threshold frequency, right? So threshold frequency is the minimum frequency above which all the frequencies give you a photo emission. Let me say it again. Threshold frequency is the minimum frequency above which all the other frequencies give you emission for that particular piece of metal, right? Now look, this is all dependent on this 6, right? So if you change the metal, right, the threshold frequency value changes. So threshold frequency might look like the property of a wave, but it actually is a property of the metal. Okay. Right, so this is basically what threshold frequency, but this is also what minimum frequency. Okay, fine. Now 1 by lambda, basically what? 1 by lambda, right? So energy is also proportional to what? 1 by lambda. Why? Because energy is equals to hc by lambda, correct? Where h is the Planck's constant. Now this is no emission, no emission, no emission, no emission, no emission. The minimum 1 by lambda, right? All the other values of 1 by lambda that are larger, right, will give an emission, right? So in this, since we have 1 by lambda, this will be reversed, right? This is the maximum wavelength. This is the maximum wavelength, right? Any other wavelength above it. Look, all of these 1 by lambdas are lower than this 1 by lambda. All of these 1 by lambdas are lower than this 1 by lambda, correct? So all of these lambdas are essentially what? More than that, right? More than that. Okay, fine. So basically, more than this, right? So basically what we say is that this is the maximum wavelength for which you get an emission. Beyond that, larger than that, you will not get an emission, right? Below this wavelength, you will get an emission. So let me re-illustrate what I'm trying to say, right? For frequency more than the threshold frequency, you will get an emission. Understand? Right? Because threshold frequency is the minimum frequency for which you get an emission, right? Understand? Okay, fine. Now some materials say greater than over here, some materials apply an equal to over here, right? Depends. Let me give me a minute. I'll come to it. Right? Okay, fine. Now, in a similar fashion, right, what we can say over here is similarly, right, threshold frequency. Threshold frequency is the maximum frequency, right? Threshold wavelength is the maximum wavelength below which you get emission. Okay. So now I was coming to the part where I told you that, okay, so essentially whether when the frequency is equal to threshold or the wavelength is equal to threshold, emission happens or not. Well, it is up for debate, right? It is up for debate. In an ideal scenario, we will say yes, it does happen. Okay. In a practical scenario, we are not so sure because essentially the electron comes over here, right? There is already a voltage applied, so that can pull it. In that case, it will happen, right? Okay. In the practical scenario, right? However, if the voltage is very low, right? Or if the voltage is negligible, we have enabled by providing the 6 minus 6, the providing energy of 6, we have enabled the electron to come out of the nuclear pull. But what about giving it enough energy to reach from here to here, right? So we literally cannot measure it. So we literally cannot comment about it. Understand? Right? So in different sources, you would find different things, right? I think theoretically we can say that yes, more than equals to, right? But it is more accurate to go this way. This is much more accurate, right? Okay. But if the question mentions more than equal to, then we go with more than equal to. Okay, fine. Now, what is this over here? Plotting kinetic energy versus frequency. This is super simple. Why? Because we have this here, h nu minus h nu naught is equals to kinetic energy, right? So what are you trying to measure? You're trying to vary the frequency. You're trying to vary the frequency. Okay. You're trying to see the variance in the kinetic energy of the emitted electron. Okay. Now, if you're trying to change the radiation and trying to measure how fast or slow the electron got, right? You would be insane if during this experiment you change the metal as well. Because then you cannot relate the two, because we can say, okay, the frequency changed, so this changed this way. But during this experiment, if you change the metal as well, right, the whole experiment became senseless. So we have to keep the metal same throughout the experiment to change this and measure the effect of this change in this kinetic energy. Now the point is, if we do not change the metal, this essentially becomes a constant, because remember, these threshold values are properties of the metal, not the radiation. Okay. And if we are plotting this on the x-axis, this becomes essentially what? Hx. This becomes a big constant, so I'm just putting a c over here. This gets plotted on the y-axis. This is what we have. And now if you look carefully over here, right, this is resembling y is equals to mx minus c, right? And the graph should something look like this. Let's extrapolate it. Okay, yeah, okay. And what should this length be equals to? This should length be equals to what? H nu naught. But we don't draw the part over here because the part over here does not exist. Think about it. This is the part where the frequency is less than threshold frequency. We do not have emission. We do not have electron. So we cannot talk about the kinetic energy of the electron. So we do not plot that part here, right? Obviously, this is nu equals to nu naught. The frequency incident is equals to the threshold frequency. And beyond that, you have a constant slope. You have a straight line with a slope value of Planck's constant. Okay, so this is what we have. Let's address a couple of questions. The threshold frequency nu naught for a metal is this much. Okay. Calculate the kinetic energy of an electron emitted when radiation of frequency this much hits it. All right. Okay. So what do we have already? Let's talk about it. All right. So this is what we have. Fine. So we know the radiation, right, that hit the metal, right? Okay. So we basically know this thing. All right. Minus what do we have? We have essentially what we have, the threshold frequency. So we have this thing. This and this is a constant, so we know this as well. And the question is asking kinetic energy. Oh wow, so this is a very straightforward question. I'm giving you 10 to 15 seconds, right? Solve it out, right? What do you have to do here? You just have to put the value of Planck's constant. In fact, you can take Planck constant out as a common, and what do you have inside? You have, I'm writing this as 11. 11 into 10 to the power 14 minus 6 into 10 to the power 14. I hope you guys have calculated it by now. This becomes essentially what? 5. This becomes 5 into 10 to the power 14. This becomes 10 to the power minus 20. And kinetic energy becomes equal to what? 6.626 into 5. Instead of 5, I can write 10 by 2 multiplied by 10 to the power minus 20. This essentially becomes your answer. Okay, fine. This was super easy, but I think you got a gist of how the problems are going to look like. Not that difficult. Okay, fine. Okay. Now the point is, right, what will happen is that many a times, the electron that we are talking about, right? We talked about the work function being the energy required to pull the most loosely held electron, right? Okay. So turns out that there is an electron that is not the most loosely held. So it does not require only 6. Let's say it requires 7. Okay. So let's say you provided 10 and actually the kinetic energy came out to be 3. All right. Now let's say instead you actually provide, in a different scenario, you actually did hit the most loosely held electron, right? And basically got, the answer should have been 4, but turns out the answer over here is coming out to be 2. Why? Because this electron needed 6 to get out. You provided it 10, right? It should have come out with 4, but instead, in its way coming out, it made some collisions to other particles, right? Other electron, other nuclei, don't know what, right? Could be anything. So in those collisions, this electron lost some energy and it came out with 2, right? Okay. Let's say another case was that this basically we provided this and we expected this, but the electron came out with 0 kinetic energy. Why? Because it had 4, it should have come out with 4, but it lost all the extra 4 just coming out. Just by the verge it came out, right? By the time it came on the verge of coming out, right? It lost all the extra energy, right? Okay. So this is the minimum. This is the minimum kinetic energy of any electron that is getting emitted. Understand? Okay. Similarly, what we calculated as 10 minus 6 is equals to 4, that is the maximum kinetic energy, right? The electrons, all of them are not going to be of the same speed, or rather the same kinetic energy. They are going to fall between the 0 and K max, right? Some will be faster, some will be slower, but the range is defined between 0 and K max. Okay. So this is what we have. Let's look at one more question. When a radiation of frequency this much hits a metal, all right, the electron is released with a maximum kinetic energy, all right. Calculate the threshold frequency nu naught for the metal, all right, fine. So we have essentially what? We have basically this thing, when radiation of this thing hits a metal. So this is what? This value, okay. We already know this, right? We also know this, all right. We already know this as well. We have to find out this. We have to find out this is equals to kinetic energy, right? Max. This is also what we know, right? Now, whether an electron will come out with what kinetic energy between 0 and max, that is not in our syllabus. So we can either calculate the K max or we can declare that this was the slowest electron, just those two extremities. We cannot calculate whether the electron is going to have a particular kinetic energy in between and what will be that value. We cannot calculate that. In our syllabus, that is not there, right? Okay. So whenever we have maximum kinetic energy, do not get scared. You have to use the same formula that you have been using till now. I'm not solving this question. I'm just blabbering here, just buying you guys time because I hope I'll check it later after the session. I hope by now some of the folks have started replying the answers over there, right? Okay. All right. So there is one more unit of energy that we need to consider now, that is EV, right? So 1 EV can actually be written as 1 E multiplied by 1 V, where this V is the volts and this E is basically what? 1.6 into 10 to the power minus 19 coulombs, and this is 1 V. Now what I'm going to do is I'm going to actually take this number alone and take the coulombs over there. So I'm going to have 1 coulombs multiplied by 1 volt. And to those who do not know, and don't worry, I don't expect you to know, 1 coulomb into 1 volt is equals to 1 joules, right? Okay. This is essentially equals to these many joules. All right. Now there's one more important thing, that is the title of this slide, that Hc by lambda expression in terms of EV, right? So what do we do here when we talk about Hc by lambda, right? What do? We have essentially what? We have 6.626 multiplied by 3 multiplied by 10 to the power minus 34 multiplied by 10 to the power plus 8 divided by wavelength in meters, right? Okay, cool. Now what you can do is, you can essentially, you know what, this over here, this is in joules, okay? Now essentially what you can say is, you can actually write this as 12400 divided by wavelength in angstrom. I hope you guys know about angstrom. If you do not, but 1 angstrom is equals to 10 to the power minus 10 meters. Okay. This is basically what? This is in electron volts. So this is over here is in electron volts. You can actually go verify. If you want to equate them to, you need to convert this EV, right? You need to convert this EV into joules. So if you multiply this thing with this number over here, as we just found out, right, you would realize that both of them are coming out to be the same, right? For example, let me just assist you over there. For example, if you wanted to verify, and let's say your wavelength was 300 nanometers, on this hand side, in the denominator, what you will place is 300 into 10 to the power minus 9 meters. This is what you would place. On the contrary, this can also be said to be equals to what? 3000 into 10 to the power minus 10 meters. So this can actually be written as 3000 angstroms. So in the denominator over here, you would place 3000. And you can see that on multiplication, both of them will essentially numerically come out to be the same. Okay. Now there's this question. Let's have a look at this, what this question is trying to say. When electromagnetic radiation of wavelength this much fall on the surface of sodium, electrons are emitted with kinetic energy of this much. Determine the work function of sodium. All right. So we know the kinetic energy. We know the wavelength, right? So what did we discuss? Right, this is in electron volt. So right. So let's calculate this in electron volt as well. Energy of photon essentially becomes equals to what? Hc by lambda. But we are not going to calculate it in joules. We are going to calculate it in electron volt. So we are going to write it as 12400 divided by 310 nanometer is 3100 angstrom. So this is what we have, electron volts. This becomes equals to what? 4 electron volts, right? Now 4 electron volts were provided. Out of that, right, sum was the work function, the remainder was the kinetic energy. So you can easily find out that the work function essentially was equals to 2.5 electron volts. Perfect, right? And this is a clear application of the units. This obviously makes numbers simpler, and many a times you will realize that, oh, 310 is a very bad number. How do I solve it out? But you'll realize, oh wow, so 310 actually simplifies the problems if you express the energies in electron volts. You're going to use electron volts throughout the remainder of this chapter. So please remember this formula. Not this part, right? This is for your conversion. This formula. Right? Okay, cool. This is what we have. Now we have acceleration and deceleration of charged particles. Right? Okay. So let's say this red ball, right? This red ball, let's say this red ball is an electron, right? Okay. Now if you were to observe its motion, right? What is happening? It is going from here to here, right? And it is what? It is slowing down. If you notice, it is going from here to here, it is slowing down, right? So what we can say is that this is decelerating. When do you think this will decelerate? When somebody is either pulling it from this end or repelling it from this end, right? Or both. So what can we say? It is basically what? Plus charge on this and minus charge on this. On the contrary, if you notice the opposite behavior, when the ball is going from here to here, or the electron is going from here to here, not the ball, right? What is happening? It is accelerating. When will that happen? When this plate is pulling it and this plate is pushing it. Then again, negative and positive. So basically this behavior seems logical. Okay, fine. What is this? This is accelerating. Okay. Right, so what are we doing right now? Photoelectric, we have divided into three parts. The first part we have studied till now, where we studied about the radiation, the metal, the work function, the kinetic energy of the emitted electron. Second part is essentially playing with the voltages. The third part is talking about the current. Okay. So positive charges always moves from a high to a low potential. Let's talk about that. And negative charges always moves from a low to a high potential if set free being the key word. Now look, whenever, right? So what is going to happen is you're not going to be provided with positive and negative. No, not that. That is not going to happen. You're going to be provided with something like 10 volts, 5 volts, stuff like that. Numbers, right? So keep this in your mind. Higher value, your brain should read it as positive. Lower value, your brain should read it as negative. And then it's all simple. Right? So for example, positive charges if set free, right? So let's say we have a free positive charge in the middle, right? Think about where this positive charge will go. So think 10 volt as positive and 5 volts as negative. So obviously this will go towards the right hand side, which is basically what? From high to low as the statement over there suggested. Let's say you had an electron over here that will go basically from what? Towards the positive, that is where from low to high potential. Just remember that much. All right. Now, what we are going to do is we are going to get some initial kinetic energies of certain particles and we are going to accelerate them through certain voltages, right? And this is the energy that is either going to be kinetic energy that is either going to be imparted to the charged particle or that is going to be consumed, taken away from the charged particle and converted into potential energy. If you're not clear about this, do not worry. This is super simple. Let me just go into it, right? I'm not going into the whole derivation, which is total energy is initial equal to total energy final, because you don't require that. It is really, really simple. Just stay with me. We'll see about that. Okay. So let's say, right, we have this case over here. Okay. Let's say the work function of this metal plate was, let's say, 5 electron volt, correct? And let's say I incident a photon on top of it, let's say of 8 electron volt. So this electron here came out with a kinetic energy of 3 electron volt, right? Okay, fine. 8 minus 5 equals to 3. This much is clear, right? So we're going to be solving problems like that, wherein the question is not asking about the kinetic energy initial, right? Till now we were calculating kinetic energy of the electron which just got emitted. Now the question might be adding this layer on top, wherein it provides you the incident radiation wavelength of frequency. It provides you the threshold wavelength frequency or work function. Then it asks you, okay, so if I have applied this much potential, what will be the kinetic energy of the charge of the electron on the opposite plate, right? Okay. Now think about it, right? Electron going from lower as in your head negative, to higher, in your head positive, right? What will happen to it? It will accelerate. Okay. What did we just say here? Q delta V is the energy imparted or taken away, right? Is the kinetic energy imparted or lost by a charged particle while moving between the plates, right? That is not the most accurate or the standard definition, but this will help you along the way. You will best recall this kind of a definition as compared to the official definition. Since any which way we are not studying the voltages and the electric current and the other subjects that you will study in physics, I'm going very, very application based over here, right? So that you don't have to cram up difficult definition without understanding their meaning. So Q delta V mod, right? Okay. This will be the energy, kinetic energy gained or lost by the charged particle moving between the two plates. Okay. So going from here to here, we have established that this electron going from here to here will get accelerated. It will get accelerated by how much? The kinetic energy change will be essentially equals to what? Q delta V, right? What is Q? Q is electron, so minus E. What is delta V? So delta V is 10 minus 5 volts. So this is basically what? 5 volts. So it started with 3 electron volts. Right? It had an increase, right? Accelerated, increase of 5. So the kinetic energy of the electron over here, right? Electron over here will essentially be equals to what? 8 electron volts. All right. So this is what we have. Now let's consider the case B here. In this, we don't have an electron. Just for understanding purposes, we have a proton here. We have a proton which is moving in that direction. It has a kinetic energy of 7 electron volts. All right. Now think about it, right? It is moving from lower to higher. So what do you think a positive charge will do going towards a positive plate? It will decelerate, correct? So it will decelerate. Now what is that change in kinetic energy? Then again it is equals to what? Mod of Q delta V. So what is Q? Plus E because it is a proton. And what is delta V? Delta V is then again 5 volts. Doesn't matter if you do 5 minus 10 or 10 minus 5, we have a mod out of it. Okay. This is then again what? 5 electron volt. But then this decelerated, right? So if this decelerated, this kinetic energy value here becomes equals to what? This value here becomes equals to 2 electron volts. Okay. What do we have here? Let's take a look at this. We have an alpha particle. So that means the charge over here is equals to what? 2e. Remember, that is a helium nucleus, helium 2 plus. Remember that? Right? Okay. So plus 2e is the charge here. Now we are going from essentially what? Higher to lower. So this will get accelerated. Accelerated by how much in terms of kinetic energy? 2e multiplied by 5v. So essentially an increase of 10 eV. So the kinetic energy of the alpha particle finally will be equals to what? 13 eV, right? 10 eV plus 3 eV. Alright, so this is what we have. The 3 was the initial one and 10 was the imparted one, so it was 13 eV. Alright, okay. Now look, the point is, I introduced this case to you earlier, right? But actually I did not tell you what it actually was. So if we have this electron here, right, and we have created a potential, these are electrode plates, if we created a potential difference such that, right, this electron goes to the opposite plate, goes toward the opposite plate, slows down, slows down, slows down, slows down, right, okay, and just before touching it, it comes back. Right? We will say that we have stopped this electron from entering the circuit. Right? So that is why the name stopping potential. But wait, why are you stopping it only here? You could have stopped this electron right here as well, asked it to come back. You could have stopped this electron here as well and asked it to come back. Stopped it here as well, asked it to come back, right? Right? So all of these will be stopping potential. Right? Okay. Because to stop it, let's say start from here and come till here and then stop and come back, you would require a really high potential. Right? Then for this one, you would require slightly less. Then for this one, you would require even slightly less potential. For this one, you will require even slightly less stopping potential. But for the electron to go till here and just before touching it, right? Stop momentarily and come back. That would be the minimum stopping potential that you have to apply. If you want to apply a large value, that's fine, right? It would just, go look at the top here. It would just look at the top over here, right? It would just go a little, then come back. If you want to apply a large stopping potential, that's fine. But if somebody is asking you what is the minimum stopping potential, then this is the way to go. Okay, fine. So this is what we have. Now the point is, look over here, right? What do we have? We have this electron, right? Momentarily stopping over here. So what will we say? We say that the kinetic energy, right, of the electron over here is essentially what? 0. Correct? Right? So for example, let's do a quick question, right? Let's say, okay, so this was the case, and let's say this was V1, let's say this was V2, and now I'm asking you what is the minimum stopping potential difference, right? Okay, so I'm actually asking you what? I'm asking you V2 minus V1, right? Mod value I'm asking you. Okay, because I've already mentioned stopping, so I've already indicated what will be the direction, right? Whether V1 will be higher or V2 will be higher. I've already told you which one will be higher because this has to be lower because this has to be in your head negative for the electron to be repelled, right? So I only need the mod value, okay? Now let's say this electron here, right? Let's say the work function of the plate here was equals to, let's say 5 electron volt, and let's say we incident a radiation to it of, let's say 13 electron volt. So that means the electron here came out with the initial kinetic energy of essentially what? 8 electron volt. For it to go from 8 electron volts to 0, right? From it to go from 8 electron volts to 0, the delta Ke must be equals to what? 8 eV, right? 8 to 0, right? Okay, fine. In fact, the negative of that, but since we are going to, let's mod it up, right? Okay. And then we are going to further equate it to Q delta V. But then again, what do we have here? What do we have here? We have E only, right? So this is going to cancel out. So mod of delta V, which is basically, oh, I keep drawing curves. Mod of delta V, which is basically this, what the question asks, is turning out to be 8 volts, right? Okay. Now this could be anything, right? This could be anything. For example, if we have a difference of 8, this could essentially be 10 volts and 2 volts. This could essentially be 20 and 12. This could be 100 and 92, anything for that matter. But the difference should be 8, right? So minimum stopping potential or minimum stopping potential difference, both are essentially the same thing, synonymously used. And this is what the question is trying to say when it says that. Alright, so let's now look at this question, correct? So what do we have here? An electron emitted from a plate, on incidence of a radiation of wavelength 62 nanometer. Okay, right? Has a minimum stopping potential of 5 volts. Alright, cool. Find the work function of the metal plate. So how do we go about this? Think about it, right? Okay, so let's see about this. So what do we have? We have essentially what? A metal plate, 2 metal plates actually, right? Okay, and we have essentially a radiation over here. Now we see that 62, right? That is actually what? A multiple of 124. So I can easily put this value here, but is this correct? No, right? Because this is nanometer, right? What do I have to do? If this is 62 nanometers, this is essentially equals to what? 62 into 10 to the power minus 9 meters. So I multiply 10 to the numerator. I multiply 10 to the denominator, right? What do? I actually combine this and this. What does it become? 620 into 10 to the power minus 10 meters. So this becomes 620 angstroms, right? Okay. Basically, with that, what do I know? That this energy of the photon is essentially coming out to be 20 electron volt. All right. So this 20 electron volt radiation is incident. There was some work function that we do not know. If we do not know the work function, we cannot find out the initial kinetic energy. All right. Okay. What we do know is that the delta V here is 5 volts, and with that delta V, the kinetic energy final here of the electron is turning out to be 0. Why 0? Because let me ask you something. If I throw a ball up in the air and the moment it stops momentarily. What is the kinetic energy of the ball at that moment? 0. So similarly, when the electron is coming from this plate to that plate, slowing down, momentarily stopping and then coming back, what is the kinetic energy over there? 0, right? So kinetic energy final is 0. And basically this one over here, delta V, is 5 volts. So for that, what should have been the initial kinetic energy? 5 electron volt, right? How so? Let me further that, right? So essentially, what should be the delta Ke? The delta Ke mod should be equals to mod Q delta V. And if we put this value in, what is this coming out to be? 5 eV, because Q is going to be minus E, but then there's a mod. Okay. But now this is stopping, right? Minimum stopping. So this is 5 electron volt deceleration. So the electron decelerated from something by 5 to 0. Look, there's a difference, right? My marks decreased by 10, right, to 80. So what were my initial marks? 90, right? So think about it, right? Your kinetic energy, right? Kinetic energy essentially, right, has been decreased by 5 to 0. So your initial kinetic energy was 5 eV. Now we can easily calculate that the work function here is essentially, that is the answer in electron volts, is going to be what? Essentially 15 eV, right? Because 20 incident minus 15 equals to 5. Remember that discussion in the beginning? 10 minus 6 equals to 4. 20 minus 15, the work function, is equals to 5. And there we have it, the answer to this question. Let's move on. Intensity. Wow, awesome topic, right? Third part of it. Although I don't think I'll be able to complete the final closure of photoelectric effect in this session alone. Let's see. So intensity is defined as essentially intensity, right? So, okay, so before even we head on to the formula, right? Let's say if we have a bright light, right, we call it intense. We call it high intensity. On the contrary, if you have a dull light, we call it low intensity, right? Okay, so that's the primary thingy. We can also say that if we have a bright light, it has a lot of photons. If you have a dull light, it has a lot less number of photons. It's a very less number of photons, right? Okay. But the point is, the large number of photons also can be scarcely distributed over a large area and it could become a dull light. Let me say it again. Even a large number of photons can be very scarcely, very less densely distributed over a large area. And it could also be a dull light, right? So the point is, intensity is actually defined as the number of photons, right? Number of photons falling per unit area per unit time. Look, it's not like at one time 100 photons came, right? It's a train. They're coming one after the other, right? So per unit time. All right, so this is what we have. Now the point is, if we have more number of photons coming, they are attacking more number of electrons over there. Not attacking, maybe attacking is not the right word, but essentially what is happening is they are essentially providing their energy to more number of electrons. If you have 10 photons, they are let's say providing their energy to 10 electrons. If you have 100 photons, they are providing their energy to 100 electrons. If you have 1000 photons, they are providing their energy to 1000 electrons, right? Okay. Now, in an ideal case scenario where all the electrons, right, that got the energy are indeed getting emitted, you have 10 electron, 100 electron and 1000 electron in the three cases that we just discovered. Discussed, not discovered. Okay. And because of that, since this time around, right, this is per second, 10 photons per second, 100 photons per second, 1000 photons per second. All right. Okay. Let's say you took a unit area of the electrode plate. Okay. So this time around per second throughout the circuit, and let's say these electrons are indeed able to reach the other plate, right? So this time around in the first one, the current is proportional to 10 electrons per second. The second case, 100 electrons per second. The third case, 1000 electrons per second. Obviously, we cannot just say that because we don't really know whether we have a unit area, right? We have just assumed it to be. Obviously, we have not mentioned whether 10 photons per second is indeed the intensity, right? But you can always generate, the question will not always mention that, right? We are just assuming it here to understand. You know, on a general basis, what you can say is that if you have high intensity, you're going to have a higher current. And on similar note, you can say that if you have a lower intensity, you will have a lower current value reading in the ammeter, right? So current is proportional to intensity. Okay. Higher the intensity, higher the current, lower the intensity, lower the current. That's the key takeaway. But my point is, for all of this to happen, right, what should happen? Each of those individual photons, right? Each of those individual photons must have an energy to cause an emission. If you have, let's say, 5 minus 6, right? Let's say this is the work function, this is the energy of one photon. Doesn't really matter if you have even a million or a billion photons coming, right? If each of them individually is insufficient to cause emission, to cause photo emission, both the terms are correct, right? You can use either one of them. If, for example, let's say, right, let me use an analogy. let's say these atoms and their electrons, right? Let's say these are some soldiers, right, of the team B, and let's say you have your own team A of photons, right? And although attacking is not the correct term here, but let's say, right, we have a war going on between team A and team B, and there's this law to this war. There's this fundamental law to this war that only one soldier of team A can attack one soldier of team B, irrespective of whether, even if all that soldier of team A come over here head on to team B at the same time, one soldier only of team A can attack one soldier of team B. There's this law somehow, hypothetically, right? Although attacking is not the correct term because here photon is transferring the energy. Now the point is, if each one of your individual soldier is weak enough to combat and win over a soldier of the team B, doesn't matter how many soldiers you have. With this given law, right? Had there been not this law, 2 or 3 or 4 weak soldiers of your team could have taken on one soldier of the other team. But there's this law that only one soldier can attack one soldier of the other team. So irrespective of whether you have 1 million soldiers or 1 billion soldiers or even more than that, you're going to lose that battle. So similarly here, if you individually, your each photon, right, is insufficient to cause emission, to provide enough energy to cause an emission to the electron, then you're not going to have emission of electrons. You're not going to have photoelectric effect. Observe, you're not going to have a current. So all of this that we discussed, that okay, intensity increased, current increased, this is all valid when your E naught, right, E of photon we can say essentially, right, is more than the work function, right? Okay, cool. So this is what we have. So all of this is valid for that only. Now then again, the point is, as you increase the intensity, more number of electrons get released, more is the current, and that is the condensation. Now the point is, right, what do we have here? Let's look at this. We have electron current on the y-axis, radiation frequency on the x-axis. Now tell me something, right? This is saying that the electron current is constant even if the radiation frequency is increased, right? Why? Because current depends only on the number of electrons. If you have 1000 electrons, if you have 1000 let's say electrons, right? Okay, essentially the current is because of these, right? Basically, let's assume ideal case scenario. Let's say you had 1000 photons, they cause the emission of 1000 electrons, right? Okay. Now case A, right? Let's say the work function was 6 electron volts. Let's say case A, the E photon was equals to 10 electron volts. Let's say case B was equals to 8. Let's say case C was equals to 7. In all of these cases, electrons are indeed going to get released. Ideal case scenario, 1000 electrons, right? So all of these cases will have what? 1000 electrons. So the current is going to be the same. So whether you have higher frequency, lower frequency, why am I discussing about frequency and then on the top right of the screen I'm talking about energy? Because E photon is equals to h nu, right? More the energy, more the frequency. So even if you have high frequency or low frequency, right, if you have this criteria satisfied, right, that is you have a non-zero electron current over there, right, basically the current value is not going to change on changing the frequency or the wavelength or the energy of a single photon. Now the point is over here, right, what is this trying to say? Radiation intensity. Now this is talking about the number of photons in a way, right? Number of photons per unit area, per unit time. But yeah, for the conversation, we can just simply say number of photons. Otherwise, the conversation will get too clunky, right? Or every time I'm saying this big term, number of photons per unit area, per unit time. So let's just say number of photons, and automatically in your head, you're hearing number of photons per unit area, per unit time. Okay, cool. Now, the point is, let's say on a unit area, in a unit time, if I increase the number of photons, right, that doesn't mean that I'm not changing the radiation, am I? Right? Right? So what I'm trying to say is that essentially, if each one of my photons has an energy of 10 and the work function is x, all of my electrons are going to be released in an ideal case with kinetic energy max of 4. Understand? right? So the point I'm trying to make is that if I have 100 photons, there's going to be 100 electrons with this much energy. If I have 10 photons, ideally I will have 10 electrons with this much kinetic energy. If I have 1 million photons, individually each of 10 electron volt energy, right, incident on a metal plate with work function this, ideally I'm going to have 1 million electrons with this energy. I did say million, right, earlier. If I said billion, assume it to be billion. If I said million, no, don't worry. Yeah, I said million right away. Okay. So this is the case. For this to happen, then again, what should be the case? This should be more than that. Otherwise, we do not talk about electron kinetic energy if there is no electron. So if this is not valid, we cannot talk about electron kinetic energy, right? Because there is not going to be an electron over there. Okay. Right? Now there are these two more curves, right? They basically combine all of your understanding of radiation, work function, kinetic energy, number of photons, intensity, stopping potential, potential difference, acceleration, deceleration, all of that into one. So I'm going to cover these. Obviously, I don't have the time in this session. I'm going to cover these in the next session, in the beginning 15 minutes of this session. So first of all, don't be late. Second thing, come after having revised as well as solve the question. Right? Why? Because you will need all the understanding of this session to be able to solve this and solve this, right? Understand this along with me. I'm going to spend around 20 to 25 minutes onto it. Don't worry about it. But the point I'm trying to make over here is that if you understand this, right, your entire knowledge of photoelectric vector is going to be concised into these two plots, and we are going to basically consolidate everything into one. Right? Okay. So, all right, this was quite an insightful and quite a knowledge-packed session, right? I think a lot of you have burned out toward the end of the session. Do not worry. If you have any doubts, let us know. Those people are there to solve your doubts. After the session, I do look at your doubts and implement your doubts, your gaps in understanding in the next session. Don't worry. That is there for you only, and I do read it, right? All the Pandays, all the Mukherjees, all the Sharmas, all the Patels, right? I am reading your comments, right? But I refrain from mentioning you till now because it is unethical for me to do so, right? So please maintain some, code of conduct over there. Please let it be please let it be an academic environment there only, right? Till then, bye-bye. We'll meet again in the next session. Keep studying, keep practicing, and come after having revised and solved the practice question. Till then, bye-bye.